Welcome to the sixth part of the video series on functions of series. Today we're going to be introducing a new type of series called the Maclaurin series. In the previous videos we did an extensive look at the geometric series, and now we're going to be moving on to a more powerful series, the Maclaurin series. So let's dive in. The definition of Maclaurin series, a little scary at first. You'll see this f to the kth derivative evaluated at 0 times x to the kth power over the k factorial. Now I have a note here. Just know that this k is here because it represents the kth derivative, and we are evaluating each derivative at 0. So essentially your shortcut through this process is always going to be to write down every power starting at 0 and then writing the factorial that is equal to the power in the denominator. So that's always going to be constant. This x to the 0 over 0 factorial, the x to the 1 over 1 factorial, the x squared over 2 factorial, dot, dot, dot. That will always be constant. The only thing that will be changing, the input, is the kth derivative starting at the original function at 0, then the first derivative at 0, the second derivative at 0, the third derivative at 0, and so on. So we have a few special notes here that, although we're calling this the Maclaurin series as the introduction video, this is just a special case of the more general term of a Taylor series. So wherever we see this 0, essentially that means we're centering the series at 0, and that'll be called the Maclaurin series. It's a specific case when x is 0. In later videos of this series, we're going to transition to the word Taylor series, and all that means is we're going to be using the general case where x can be any value of a. And of course, because it's a more applicable solution, it's the more general case. The Maclaurin series is only when x is 0. So it's just some key terminology moving forward. Most people will use these two interchangeably at 0. They'll say it's the Taylor series centered at 0, or they'll call it the Maclaurin series. Okay, so moving forward, we got to ask ourselves, why are we even certain that the Maclaurin series, this strange formula here, why are we even certain that it does actually represent a good model for the cosine function, or the sine function, or the e to the x function as we'll be exploring? So when you're going to make the Maclaurin series, you usually want to set up some sort of graphic organizer for yourself. And here I have every k from 0 to 6, and that k is going to represent the derivative. So right here you'll see that this is the kth derivative of f, rho, and the 0th derivative is just the original function. So our original function is cosine, and then from there we're going to take the first derivative, which is negative sine, the second derivative, which is negative cosine, third derivative, which is sine, and so on. Then, because it's a Maclaurin series centered at 0, we're going to evaluate each of those derivatives at 0. So cosine of 0 is of course 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, and so on. Now the next step, all we're looking to do, because these things are constant, the powers and the factorials are constant, we will never change those. The only thing we need to do is put in the kth derivative at 0 values, these coefficients, into our series. So that 1 goes here, the 0 is with the first term or second term, the negative 1 with the third term, and the 0 with the fourth term. And what we're doing is we're looking for a pattern. So what we see is that every odd powered term, the 0, 0, and the 0, the coefficients are 0. And what's nice is after we eliminate all the odd power terms, we're only left with all the even power terms. And writing it in summation notation, we have 2k, which is the eventh power, and 2k factorial, which is the even powered factorial. So the only thing we need to remember is, of course, this negative 1 to the k for the alternating sign. And I have a note here that this should be very easy to memorize because you've known for a long time that cosine is an even function. And Luckily, all the powers of the Taylor expansion are also even, and the factorials are even. So everything's even. You just need to make sure you don't forget the alternating sign. Okay, so are we confident this method works? Well, to explore this, we're just going to use technology. We're not going to try to do an intensive, rigorous proof for now. This is just a matter of understanding this concept intuitively. So we're going to build a Desmos Explore and see if our Taylor series does indeed converge when the number of terms increases. So here I have my cosine curve hidden in a folder, and you'll notice my red curve is the cosine curve, while the green curve is my even powers over my even factorials with my alternating sign. And I'm only using one term, and one term is obviously not a very good model for cosine. But what happens as I begin to take more and more terms? So this would be 1 minus x squared over 2 factorial. A pretty good model right here at 0 because we're centering at 0, but not a very good model if you go out to, say, 5. So we take more terms. Let's look at the first 5 terms. Well, the first 5 terms is, of course, 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, dot, dot, dot. What we're seeing is starting to be a pretty good model for a longer period of x. And let's just jack this number up to quite large. And what we see is, indeed, our cosine curve and our series are becoming good models of each other. How far out is my function a good model? Well, even all the way out here to 30 and negative 30, I'm still seeing it's a good model. Now here you're starting to see my computer processing power break down because we are using 50 terms. That's a lot of computational requirement. But if I were to change this to 100 or 1,000, you would continue to see the interval get larger and larger where these two series and functions are convergent on each other. So what we're seeing from this technological exploration is, 1, this Maclaurin series formula works, and 2, when we do it, we end up getting a very large interval of convergence. It looks like the more terms I'm using, the larger my interval becomes. Matter of fact, it might look like every single value of x is contained within the interval of convergence. Even if I go all the way to negative 30, the cosine curve and the series are identical. And that would be true even at 50 if I used more terms. So going back, we see now it does seem they converge, and it does seem they converge for all values of x, which is nice. Can we do now with our intuition built, a more rigorous proof of that convergence radius? So when doing these, especially because of the factorials and the powers involved, a nice convergence test to use is the ratio test. So a review of that is that we're looking at the next term divided by the nth term, and what happens to that ratio as the number of terms goes out to infinity. If it's less than 1, it's converging absolutely. Note that the absolute convergence will be a topic for a future video. For now, just consider that any absolutely convergent function is also just converging. So focus on the word converging here, and we'll come back to absolutely at a later time. Equals 1 is inconclusive. We'll use a different test. Greater than 1 is divergent. So we apply the ratio test using our series for cosine. We take the nth plus 1 term power over the nth plus 1 term factorial. And the reason why the ratio test works out nicely, when we multiply by the reciprocal, well, the 2n factorial cancels all of these factorials, leaving only the 2n plus 2 and the 2n plus 1 term. And the x to the 2n power cancels the x to the 2n power, leaving only x squared. Now, a lot of students get stuck here because they forget to write the limit down. If you don't have this limit here and you're looking at this expression, it's not clear what happens. But if you write the limit down, you'll see, oh, x is constant because the only thing changing is n. And if n is getting larger and larger while x remains constant, this limit will become 0 no matter what x is. In other words, any value of x you choose, any real number, as n approaches infinity, this will approach 0, which is always less than 1. So we have shown now that the cosine curve and its Maclaurin series are convergent for all real values using the ratio test, which is quite nice. And we've even shown it's absolutely convergent, which is an even stronger case. Okay, so moving forward, I have some practice for you. You are going to replicate this process for sine and e, and in the next slides, I'll be going over the solutions. Hey, so hopefully you've had a chance to work on this on your own. I'll quickly run through the solutions here. First thing is we use our graphic organizer for sine. We map out all the derivatives. Then we plug in 0 into all those derivatives, and we plug in our coefficients into our same formula here. Keep in mind the x's and the factorials will always have the same look. The only thing changing are the coefficients. After this, we see all the even terms happen to have 0 as a coefficient, leaving only the odd power terms over the odd factorials with an alternating sign, which should be easy to remember because sine is odd and all the powers that are left are odd and the factorials are odd. Easy to remember. Don't forget those alternating signs. Then we want to know, are we sure this series holds? So we plug it into our Desmos calculator, make an algorithm out of it, and we're going to see whether it seems like they're convergent. So if I look at my sine series I created, I start jacking up the number of terms. These are indeed seeming to converge to each other with more terms, which is nice, and it appears that it's done for all real values. So how do we show that analytically? We use the ratio test, and using the ratio test, once again, if the nth plus 1 term over the nth term, looking at the limit as n approaches infinity, we end up getting a similar situation where x is constant divided by an infinitely large value, which is going to be less than 1 for all real numbers. So our intuition from the technology also matches our ratio test, which is good. Then we do it for e. Now for e, it's a little easy because all the derivatives of e to the x are e to the x. Plug in 0, and e to the 0 is 1. So every single derivative of 0, every single derivative at 0 will just be 1, and the only thing that has left to be written is the x to the k over k factorial. So expanding that out, e to the x looks like this. You will need to memorize what all these series look like, so make sure you write those down a few times and convert those to memory. Then, are we certain that the e to the x and the series converge? So again, we use our Desmos calculator to see if our intuition matches what we've discovered. So we have our series for e, our function e, we jack up the number of terms, and we see that the more and more terms I use, the two things become convergent, seemingly for all real values of x. So that's nice. Can we indeed show that using, analytics? Yes, we get the ratio test, the next term divided by the previous term, take that limit as n approaches infinity. Again, you're only left with x, which is constant, divided by this increasing value of n, and a constant over a increasing value will approach 0 for any value of x. So it does converge for all real numbers. So our three series that we've looked at all converge for all real values, which is quite nice. You will need to have those memorized, and we will be looking at those in more detail in the next video, applying some cool tricks and making some sweet discoveries. Okay, hope you enjoyed the video, and I'll be posting the seventh part of the video in the near future. Thank you.